So the idea, roughly, the idea is that means a change of category. We try always to strive to deepen the knowledge, the level of the knowledge, or the refinement, or whatever. On the other hand, we don't always stick with the most refined, because we back up to a much coarser picture if that's sufficient for a certain purpose. And we also back up in another way when we approximate solutions of partial differential equations by means of the finite element method, numerical analysis, and so forth. So the idea is that in general, all this kind of different levels or degrees of cohesion is analyzed as a series, or not a series, but a system of categories. It isn't just one category. It needs to be a system of categories. When you make a qualitative change in the depth, change from one category to another, but let's say most of the time you stay within one category, you go to another one. So there are these two kinds of motion. So that's what I'm trying to explain. Also, of course, in general, the idea is that traditional philosophical notions for thousands of years could be given a mathematical formulation sufficiently general, using the most up-to-date technology we have in mathematics, i.e. topos theory, etc., could be given a formulation which in some sense almost fully captures the philosophical content, not just some fragment of it, and so that philosophical considerations could become open to some degree to calculation, as Leibniz, for example, dreamed. So the first idea is to distinguish between generalized spaces. I've just called objects of these categories spaces to distinguish them from maybe other kinds of categories where you might speak of algebras. Spaces, a space I remember in my early days of my collaboration with Steve Shanuel, I was trying to explain something to him, and I said, let X be a space. And he said, well, what kind of a space? Give me a topological space? No, just a space. What's that? Well, it's an object in a spatial category. Oh, I see, okay. But the point is that response is actually very meaningful. But at first glance, it might seem as a mere verbal circumlocution, but it is actually so. In a way, the idea is to define what is a category of space. It's a category, but it's a special kind of category, and then we can just say a space of this or that category. So we need to distinguish between the spaces themselves and the categories in which they live. Okay. It is often said that the basic idea of a topos is that it is a generalized space. In fact, both historically and in terms of intrinsic content, that is an oversimplification. An oversimplification that has distracted the attention of category theorists and so on, from the development of a useful class of toposes, which can be more accurately described as consisting of objects that are generalized spaces, objects in the category, rather than one category being the thing. In order to display more sharply the contrast, let me first survey briefly some of the kinds of generalized space that are, after all, related to individual toposes. Of course, the original connection between spaces and toposes was via the Lawvere-Lazard notion of sheaf, which came up in order to generalize and systematize well-established experience in the field of complex analysis. To generalize from the complex spaces to the supposedly default nation of space, quote unquote, which is based on a partially ordered set which satisfies conditions appropriate to open regions of space. Partially open set of open regions as a basis for the category of sheaves. So it's so-called localic topos. This was the first kind of generalized space. But in fact, the sheaves first appeared as linear sheaves, and in analysis even today, linear sheaves are the most frequent. Sheaves of functions and vector bundles and so forth and so on. Although it was recognized already in the 1950s that these linear sheaves are very effectively considered as linear objects in the nonlinear category of set-like sheaves. Hence the notion of topos, basically, or that was one of the origins of the notion of topos. Now these sheaves, the original sheaves, have a dual description. They are either local homeomorphisms or they are special presheaves. Presheaves of sections which always satisfy so-called sheaf conditions. The two descriptions, at one point, Grothendieck said we have to forget the local homeomorphism point of view because in the generalizations that we want, the presheaf point of view is the only one that works. Of course, it turned out that the local homeomorphism description did generalize quite a bit too. But basically, one point is that in terms of the presheaf point of view, that's always accompanied by the sheaf condition, compatibility with coverings. And this principle of compatibility of coverings was clearly a good generalization because it not only held for pure topology, but also for smooth and analytic geometry. In other words, the fact that the map or a section or something is smooth on each part of the covering implies that it is smooth, or even better, if it's given on each part of a covering in a compatible way, that it even exists globally. That if and only if, which is known as the sheaf condition, was applied equally well to analytic, the existence of analytic and smooth as well as continuous. And it was found out by Sayre that it also worked in algebraic geometry, which applies to polynomial maps. Well, perhaps the first and most obvious generalization of this kind of category of sheaves was something almost opposite in a way, namely the actions of a given group on discrete sets. Because this was very appropriate because actually groups and traditional spaces live in the same world, because with the space you have universal covering space, but you also have the Poincare groupoid, fundamental of the groupoid, of the Eilenberg-MacLane spaces and so forth, which has to do directly with the interaction of groups and traditional spaces, part of which can be explained better if it takes place in one category. So one needed to generalize the notion of space from topological spaces at least to the level of permitting groups to run around as objects in the same category. So within the general setting of toposes, which is much, much more general, Grothendieck first isolated a small part of it, which he called the étendue, which contains both the sheaves on the poset of regions as well as the actions of a group or a groupoid. Those two fairly disparate kinds are united under the notion of étendue, which is most simply described simply as in the appropriate language as a topos which is locally like sheaves on the poset of regions, which it turns out includes the group. in an apparently laughable way, namely, the group is locally a one-point space, which analysts like to amuse people by saying, consider, the group acting on a one-point space. This has a lot of information in it, despite the apparent triviality. But that content starts with the connection which I have said. So Grothendieck defined the notion of étendue as a topos that is locally of the kind defined by a poset of open regions, and it turned out that an étendue is always obtained if more generally we start with a category, a site, which as a category consists only of monomorphisms. If every map is invertible, i.e. a groupoid, then of course everything is a monomorphism. On the other hand, in a poset, everything is trivially a monomorphism, so that's obviously a generalization. It takes a few minutes to realize that such a thing is locally, in the appropriate sense, a poset. And so, but then conversely, it turned out that any Grothendieck topos, which is locally like the sheaves on a poset of regions, does in fact have a site which consists of monomorphisms. Okay, but on the other hand, one has to keep in mind that these so-called generalized spaces are not just the topos, the sheaves on them, no more than the lattice of open regions itself determines the space. Because if it's a smooth space, or an analytic space, or an algebraic space, and so on, there is, in addition to the poset of regions, there is always the sheaf of local rings. That's why one talks about ring toposes, and it's absolutely essential that you have this kind of topos, this kind of topos, together with a ring object in it, or you lose completely the connection. The product, for example, with the pure toposes is not the same as the product in the category of pairs consisting of toposes equipped with rings. So, in particular, that's a simple example of that. The spectrum of a ring is not a topological space. It's not the Zariski. People study that space, but it's really only just in a very poor way connected with the scheme, because at least as essential as the sheaf of local rings. So when one pushes the picture down to a single space in that way, an additional structure is created which has to be carried along with it. So the sheaf of holomorphic or smooth functions, which of course is incorporated in a linearized theory, provided we construe it as being a monoidal abelian category and so on. But the fact that the product of underlying toposes or underlying topological spaces is quite different from the product of schemes means that an algebraic group is not a topological group. There is no underlying topological group for an algebraic group, just because the notion of group depends on the notion of Cartesian product, and that's not preserved by this forgetting process. So, I think, by the way, that in the case of algebraic geometry, that mismatch can be considerably alleviated if one considers that the base topos is not, after all, abstract sets, but rather the Galoisian topos of sheaves on the category of finite field extensions, which reduces to abstract sets only in case the ground field is already algebraically closed. Because by working in that which is a Boolean topos, working in that Boolean topos instead of an abstract set, one gets a much better match with the geometry. That remark, elaborating that remark, you see, is really only a fragment of a task which category theorists have been avoiding for too long. That's the task of the refoundation of algebraic geometry, taking into account the most up-to-date insights from category theory, based, of course, ultimately on Grothendieck's pioneering work, but not stuck in the archaic formulations that it was given. Grothendieck's formulation, despite the last 50 years of work by algebraic geometers, has not been much developed. It's only been applied in its original formulation, something approximately its original formulation. And so it's long overdue for clarification. And this remark of mine that the basic ground topos, basic foundation, if you like, should not be Cantorian sets, but Galoisian sets. This is just a beginning fragment of that. Now, already in the 1950s, the first topos to be considered explicitly as a category, which was simplicial sets. In 1950, actually, simplicial sets were introduced as a category. It happens to be a topos. It has many properties as a topos, which again, there's a long overdue task to explain not only is it a topos, but what are the special properties qua topos that it has. Because the homotopy theorists who work with it don't know these properties, they just use them unconsciously. In any case, when it was first introduced, it's interesting to look at this paper by Eilenberg and Zilber, because the first line of the paper says, you have to understand that these are like spaces, but they don't live on their points. Words to that effect. They don't live on their points. This was in spite of that, for years afterwards, people continued to think that spaces should live on their points somehow. Just completely should have been considered overthrown at that point. And not just for combinatorial spaces, but for all kinds of spaces. Slowly. Even more strongly, Grothendieck's 1960 techniques for construction of analytic spaces heralded the realization that categories of space need objects, i.e. spaces, for which any description as topological space plus something else was awkward if not imprecise. In the ensuing half-century, simplicial sets have been extensively studied by algebraic topologists, led by Kahn, but the category theorists have developed only in a rudimentary degree the precise distinguishing features that simplicial sets have qua topos. Perhaps I should report here that finally, after 50 years, I met Kahn last month. Daniel Kahn. He doesn't go to meetings. He told me that he has worked for 50 years and more on nothing but combinatorial homotopy. This is his strength, that he doesn't let himself be distracted by other questions. But it was just 50 years ago this year that his paper on adjoint functors was published, and it's had a tremendous effect. Certainly influenced my work a lot. Probably everybody's work, even the work of logicians. So he told me the story about how how the adjoints came about, which is kind of interesting, perhaps. First of all, Kahn himself is from Holland. He's a good friend of Ike Mertijk, for example, and I didn't know that. But his entire graduate career consisted of 2 months. He was working in Israel. Kahn was working in Israel, and Eilenberg stayed for 2 months in a hotel in Jerusalem. Kahn was already independently interested in combinatorial homotopy, so he went and talked to Eilenberg about it, and Eilenberg gave him a problem. He went home and solved the problem, came back, had another problem, blah, blah. So after 2 2 months, he had enough for a thesis. So then he applied to graduate school and entered the PhD program, translated the thesis into Hebrew, which would be, necessary, and then got his degree. So this was his entire graduate career, was those few minutes were required to translate the thesis. He applied and got admitted, and anyway. So, but then he came as a postdoctoral fellow, or whatever they called it then, to Columbia, where Eilenberg was. And one day Eilenberg and Kahn and also Abhyankar, algebraic geometer, were discussing various things, and Eilenberg remarked that the tensor product functor is determined by the Hom functor up to isomorphism. Given the Hom functor, then there could only be one tensor product functor. Whereupon Abhyankar said, I wonder if the converse is true as well, that the Hom is determined by the tensor. Whereupon Eilenberg said, of course not. That's ridiculous. How can you say a thing like that? Which made Kahn so mad he went home and discovered adjoint functors. So one shouldn't be too fast. Oh no, one should be fast because it makes people mad and sets them in motion. Anyway. And of course the word adjoint was put onto it by Eilenberg. Again, there's a persistent mythology to the effect that the notion of adjoint functor is modeled on adjoint operators in Hilbert space theory, that sort of thing. Kahn says, absolutely not. He didn't even know what an adjoint operator was in those days. Just, as I was saying, his actual mathematical education was rather narrow. Of course, he eventually learned all kinds of things, but at that moment he didn't know, never heard of adjoint. It was just, with Eilenberg, saw some analogy and read it. Okay, well, to come back then to the generalized space, no doubt the most important example of a topos which, together with the needed linearizer heap of rings or whatever you want to put together, the example of a topos which is treated as a generalized space is the étale topos of a given scheme in algebraic geometry. This is something that's not needed in analytic geometry or C-smooth geometry, because in those two cases you have the implicit function theorem, and you can just talk about local homeomorphisms. But in algebraic geometry you do not have implicit function theorem. In other words, just because the derivative of the map is invertible does not mean you can even, square root is not an algebraic polynomial function, even though it should be invertible, locally invertible, not globally. We're just talking about local. So the local homeomorphism condition in algebraic geometry was too strong due to the lack of implicit function theorem. But there is an infinitesimal analog, namely, as I said, that the derivative at each point, which is a linear transformation, should be an invertible linear transformation. So Grothendieck said, well, in algebraic geometry, let's consider the objects over a base that is equipped with a map to a base, but the map has this property of being infinitesimally invertible, but not necessarily locally. Well, this now is a little category that can be used as a site, once one had the machinery for constructing topos on sites, a topos which clearly is like the variable sets over a poset of regions, but it's not a poset anymore, because all these étale objects over a fixed object form a very nice little category. It's not a poset, however. Nor is it locally a poset. It's not an étendue. You don't get an étendue this way. Instead, we get something almost opposite. Because if you consider, it suffices as a site to consider connected, even just rings, rings, with no those connected spaces, connected schemes over the given scheme. which are moreover étale, moreover have this infinitesimal isomorphism property. So this category of connected étale objects has a very interesting property. If you have two morphisms which agree even on a very tiny piece of the domain, then they're equal. In other words, a tiny piece is a map which is always epimorphism, no matter how tiny it is. So, but that's a typical map. So every map in this little category, the category thinks every map is an epimorphism, or it's the other way around. I don't know how much thinking a category can do, but I say thinking and so forth because when you look inside the topos, these maps are not epimorphisms. Epimorphism is a property universally testing cancellation and so forth. If you just test against other étale connected objects only, then you have this cancellation property. It's a sort of uniqueness of lifting. If you have liftings that agree at all, sort of like an initial condition, agree at all, then they're uniquely determined. So that means that you have a site in which every map is epic. So here we come to another interesting connection with logic. Peter Johnstone had shown independently of all that, well, I suppose I don't know what went into his thinking, but that there are certain toposes which include the sheaves on a post set and the actions of the group, include those two cases also. Different common generalization. But the property that they have is that the get my name. Okay. What Johnstone calls QD, which I've called various things. Today I'm calling it adequately separable. So the idea is that an object A in that category, actually an extensive category is the appropriate. By logicians, it's called decidable. So that's where the D comes from. That means that if you put it by the diagonal map inside its square, that there exists a complement. This is the conclusion. There should exist another inclusion so that A squared is equal to A plus A prime along these actual maps. So in other words, in a topos, every subobject has a so-called complement movement. It's a hiding complement, meaning that the union, although it's disjoint, the union of the two things may not be the whole thing, right? So you could say Boolean complement, as opposed to the hiding complement becomes a Boolean complement, or just, since we don't need the hiding operation in general to discuss this, just that there should exist another subobject which is both disjoint and the two add up to everything. Now, again, in a topos, it's easy to see that if every object were separable, then in fact every object would be Boolean. It would be a Boolean topos. Truth values would be 1 plus 1 and so forth. But in many toposes which are not Boolean, there are still some objects which have this property, which we call, as algebraists, we call it separable, because it corresponds to, in number theory of polynomials and so forth, to separability. The idea, if you have the space of solutions of a polynomial equation, if all the roots are very distinct from each other, then it's called separable. You see, so it means really that in the space of pairs of solutions, that any two are really very distinct. By contrast, in most objects, the diagonal sort of has at least an infinitesimal glue with the rest. And so that's detected in algebra by the fact that if you have repeated roots of a polynomial, like say x squared times x minus 1, it's a cubic equation, it only has two bare points as roots, but one of those roots is actually sort of double, so there's a bit of an infinitesimality there. And it no longer has a clean diagonal. You can even develop a whole terminology about being clean. You see so anyway, the quotient part, or the adequacy part, means that every object has an epimorphic image of some decidable or separable object. Since this condition is obviously closed under arbitrary disjoint sums, it's equivalent to say that the topos has a set of generators which are separable or decidable. Generating and adequacy is it expresses the idea that you're generated up to fullness of Hom sets. So if you can use this terminology with a space with a clean diagonal. If you collapse it, the diagonal gets dirty. Many analogies can be built around this idea of cleaning and smudging and so on. To try to picture how these special kind of toposes work. So, but what Johnstone showed was a topos is QD, adequate number of separable objects to cover everything, if and only if there exists a site of epimorphisms. That is a site, a subcategory which generates everything and which thinks that it consists of epimorphism. It has this cancellation property. So for example, the connected étale objects over a given space has this property. So in other words, this second idea of generalized space, which includes the key example of Grothendieck, even though his generalization didn't, they're both toposes. The étale topos is included the petit étale topos is included among these things with epic sites, whereas the étendues were things with monic sites. So now we have these two generalizations of classical spaces, or even of groups and open sets, both of the common generalization of both. They have a still further generalization. Well, obviously, there's an obvious one, sort of bi-cancellation property. Namely, if you have two parallel maps, you can conclude that they're equal, provided, followed by something, they're equal. And if that alone were sufficient, you would say what? That F is monic. If F were monic, this would certainly be true already. But also, if there existed an X so that AX equals BX, if that were sufficient, you would say that X is epic. Well, maybe you're in a category with the property that not everything is epic, not everything is monic. Nonetheless, if you have both of these hypotheses, for emphasis, I can put an existential quantifier at no logical cost, since those variables don't occur on the right. So this is a bi-cancellation property. Toposes which have a site like that are a reasonable candidate for the idea of a generalized space. I should have said, of course, that it's also the opposite sort of idea is common, namely that any topos is a generalized space. And this point of view, of course, has many virtues, but I'm saying that there's a more immediately connected with classical ideas of space are these things. Well, now this, okay, like let me just say that like the monic, by that I mean categories, all whose maps are monic, or those which are epic, or the bi-cancellation ones, and so forth. These are all categories of categories which are reflective. So, given any category, you can, in a universal way, force them to have this property. This obviously induces a congruence relation on the Hom sets of the category. So even if it's not true, you can force it to be true, and that's the left adjoint of the inclusion of the bi-cancellations into the reflection preserves products because it's a general feature, because if I take one of these things, say A, and look at the functor category, A to the C, where C is arbitrary. This is still in the same subcategory. If A consists entirely of monics, then A to the C also, for any C, no matter what the shape of C is. Or if I have the bi-cancellation, etc., etc. Or, obviously, also posets. I should have started with that. It's well known, right? If you take a category, you just apply an existential quantifier. You replace the whole Hom set by 0 or 1, according as whether there were any or not. That's the associated poset. So that's the reflection into posets. And that product not only is the inverse limit of poset to poset, but even a poset to any category power is still a poset. And that means that the reflection process preserves products. Preserving products is very important because it means that you can push down algebraic structure that depends on having its domain, the structural operations having their domain be products and so forth. And again, the same thing is true of groupoids. Groupoids, sort of the fundamental groupoid of a category. You just force every map to be invertible, which of course might involve killing the category. But anyway, there's a universal way to do it. So, well, this is, if you like, the technical point, but it's interesting to see this one is trivial to verify, but it's equivalent to the fact that the reflection preserves products, which is a little bit harder to compute if you have to do a lot of equivalence relation checking and so forth. When you collapse, you have to impose the congruence relation. It's the congruence relation that's generated. Anyway, this is technically useful because if you wanted to define the T-topos associated to a space, that is to an object in a cohesive topos, try to mimic the classical constructions of from a space finding the little topos. This one of the steps should involve, I think, this reflection. Forcing the site, given the site, slash it by a given x. That's another category of the same type. I mean, yeah, this is equally important. Not only have this closure property, but if you have a discrete vibration over something, discrete vibration, and the base is in one of these categories, subcategories, and so is the total space. And this this localization, of course, is a discrete vibration. So, yeah, that's to such a program. That's an equally important closure point. At the moment, I'm considering these classes as candidates for generalized space, you see, so these are properties that they should have. Well, I got to thinking, well, really, this is sort of complicated. There's something that this obviously implies, even more general than any of these, but still very restrictive and applicable to all the examples. So that's a good kind of thing, right? It's simpler, more general, and yet it includes all the examples. What could be better? Anyway, so that's what today I'm giving it the fanciful name empty. Now, what I mean is this. An object, it's about idempotence. An idempotent, of course, is an endomap whose square is equal to itself. And I want the axiom which says this equals 1 sub A. So I'm calling A an empty object if it has no idempotence. The colloquial use of the negation no, you see, is not the one that logicians use. It simply means it implies a trivial case. Instead of implying false, it's implying a trivial case. So it's a well established to call this no idempotence. So an object that has no idempotence, you see, in particular, it means it has no global point. So you suppose you had a terminal object and a global point. Well, of course, the unique map here, followed by that, and the point gives rise to an idempotent. Thank you. Yeah. Of course, in a category with a terminal object, a point in the most narrow sense of point, i.e. a map from 1, trivially gives rise to an idempotent. So if A is empty, it doesn't have any points in particular, but it doesn't have any degeneracies. A better way to think of it, perhaps, is, a general map in a category I sometimes call a figure. This terminology for later as well. Figure of shape A in the space X. And this is slightly more than just another name for map, because I require that, well, let's say it this way. This is a script A figure if A is in A, where in principle A is just some class of objects, later to be specified. But so a figure, there's a terminology which I will take over from topology again, simplicial sets, the 1950. If you talk about degeneracies, a degenerate figure is one such that there exists an idempotent, which leaves it fixed. Degenerate. Well, I mean, in other words, it's really degenerate if E is not 1. So this is the degeneracy of this is the very clear ancient geometric usage. The shape of a triangle, for example, might have a singular realization. A figure is called singular if it's not a monomorphism. Singular is general. But the very special kind of singular is to be degenerate, i.e. to be a monomorphism in the sense that it factors through a non-trivial idempotent. That's the sort of thing, if you have a triangle index means a figure of shape, the generic triangle, yes, but that shape might be degenerate and the triangle really collapsed to a line. The idea of collapsing a triangle to a line. Or a degenerate path would just be a point. Or even a path which happens to be a closed path is degenerate to the extent that, well, is that right? Yes. So the particular way that the idea is that any of these toposes of generalized spaces of a certain. Any topos which represents a generalized space in the sense that this generalized space is parameterizing discrete sets. Okay, I didn't say that, but that's the idea of what these petit toposes are. They discrete spaces parameterized smoothly by something, and the something could be a group, it could be a classical space, it could be an étal space, but among those there will exist an adequate family of figures with no degeneracies. So you have G sets generated by a group. Group doesn't have any idempotency. Poset, there aren't even any endomorphisms, let alone idempotency in the poset itself. But it's true for even the most general thing that I've mentioned, that though there might be endomorphisms, there are no idempotent ones. Okay. So this very simple condition that there should be a site consists of empty objects, i.e. objects that have no retracts. And hence no figure is really degenerate. No degenerate figures. Because if there's no way to degenerate them and the figures are those kind of objects, then there are no degenerate figures. So that seems to be the most general notion of. So we can add that to the list. Because trivially, it's easy to see that this again has these two properties. If I take a category with no idempotence, raise it to any power, it still has no idempotence. Because the natural transformations in a functor category are basically calculated in the values, and the values have this restriction. And again, same with discrete vibration. The maps, the discrete vibration, are labeled by the maps below, and they compose that way. So if there's no idempotence below, there's certainly no idempotence above. And so there's a reflection. In other words, here's a problem for computing. You could take any small category, even say a finite category, you can force it to have no idempotence in a universal way. How do you calculate that? In principle, it's clear that it exists. But what is it in a concrete case? Because it's very, I guess, kind of hard to understand how the calculation should go. To generate, you have to generate an equivalence relation, to generate a congruence relation on the category, starting from the fact that any idempotent and the identity have to be identified, and you have to close under composition. Making those identifications, you might have created more idempotents, so it sounds like you have to go through a sequential construction. Now, there are some examples where it becomes easier, but still not obvious. I'm not saying it's hard, it's just that they don't know how to do it. Maybe someone can figure out. I hope someone will figure out how to compute the idempotent-free reflection of the given. There are a lot of categories in which you have, it's the same as inverting split. You can sort of, without loss of generality, always assume that a category has splitting of idempotence. Any idempotent splits into an epi followed by a mono. You could explain the idea of degeneracy in terms of that instead, for example. Maybe more effectively. And it would mean, you see, that the figure itself factors through that quotient. Or is it? What am I saying? So there are many categories that have pullbacks, and if you take a split epimorphism, any pullback of it is always a split epimorphism again. So if you have split idempotents and you have pullbacks, you need not to assume any exactness properties about the pullbacks, because they're automatically true for idempotents and for split epis. Pulling back to a general epi might not be epi, but for a split one, yes. So if you have pullbacks and split idempotents, then every fraction, see, I mean, the maps in the category we're trying to construct could be called like fractions, because you go ahead, but then whenever you have an idempotent, you can also go backward, or whenever you have a split epi, you can also go backward. So it's sort of like a fraction. But in principle, fractions are words: A, B inverse, C, D inverse, and so on, right? But in case your category has pullbacks, all fractions can be reduced to length 2, because if something followed, an arbitrary thing followed by a split epi is equivalent, is in fact a split epi followed by something, and so all fractions can be reduced to length 2. Something like the calculus of fractions used in homotopy theory and so forth, in one way simpler, but it's more explicit. But on the other hand, at least at this moment, less clear how you complete it. But in anyway, the associated topos could perhaps be described in that way. Well, this is all by way of saying this is not what I'm interested in, right? I want to consider the other kind of toposes, which are about. As I say, whose individual objects could be considered as bases, instead of the topos as a whole. And so, well, if it were a mere logical negation, in other words, those are the small things, let's consider the ones that aren't small, that would mean something like this, because the other one was about the existence of a site. It would mean it's a topo such that every site has to contain some non-empty objects that have end events. But that's not a very good, and we don't really expect to take the logical complement. We want, sort of in the world of all toposes, you have now these small ones. There should be another world of large ones with a very small intersection of the two classes. And of course, the typical case is a mixture of the two. Namely, you have variable categories of spaces, variable over one base and cohesive in the other direction. The typical case is going to be mixed, so the mere logical complement is not quite what we're after. On the other hand, we can expect that that's a typical, that will certainly be a feature, that there have to be degeneracies. Somewhere there have to be figures with degeneracies in the category, which is not reduced to that. Yeah. So I use the term figure. Let me make that more precise by attempting to exercise some hostility toward the ignorance which says that objects in a category have no souls. It's a common, one of those commonplaces that many people repeat without really thinking about it. In fact, category theory is the best possible way for describing the inside of an object. With every object, we can associate a geometry. What's a geometry? Geometry is, in some very general sense, a system of figures and incidence relations. What's an incidence relation?
Let me be slightly more precise here. If I have an object, wrong page. If I have an object, I want to define the geometry of X to be the discrete vibration over A, which is just A/X. In other words, an incidence relation between two figures is just a commutative triangle. This figure alpha
Is incident on B,
if I have a proof of it, which is
commutative triangle. Of course, if beta is a non-singular figure, i.e. a monomorphism, then there's at most one proof F. But in general, we have to give the F. So,
the incidence relations.
now, of course, you might think of much more complicated things. You have two figures that intersect, and that other figure, and together with that, and so forth. But that's just a ramification
Within the same category. For example, if A has pullbacks, you can
intersect the figures, and so forth.
and so on. So it's all determined by that category, I think.
Now, here's an example you might not think of right away, but you take the notion of a convergent sequence, the limit point of a sequence. So there's a generic convergent sequence. Sometimes it's described as 1, 1/2, 1/4, 1/8, blah, 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 dot, 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 0. Whatever. You can describe it in many ways, but there's a generic commutative sequence, which could be a figure type, a figure shape.
These are just arbitrarily called figure shapes. You could take
all of these. Maybe you want to do that first. But then also, not only that figure shape, but the bare point. And among the incidence relations are the fact that this point is the seventh term in the sequence, or the infinity one. Okay. So now, a space which is equipped with figures of that type, it's essentially a sequential topological space, or a sequentially determined topological space, for example, is entirely determined by that geometry.
And if you have any map of spaces, there's a corresponding functor. It's more than a functor, it preserves the underlying shapes, the shape of the figures.
Well, what is a functor? It just maps figures to figures in a way that does not tear the incidence relations. So that
any such thing can be called a continuous map.
Because it doesn't tear the incidence relations. And if you want to picture the space, well, of course, you have to start with a way of picturing the shapes. For example, with the simplicial sets, you have the interval, the triangle, the tetrahedron, so when you picture it that way, then the general X is obviously just a complicated interlocking combination of those things. So the idea that the geometry should be picturable reverts to how you picture those things. In any case, most discussions of geometry are abstract anyway. So if you have the notion of figures and incidence relations, you have a geometry. Well, maybe this is a good place to mention another philosophical point, which is the old debate, are mathematical objects structures or not? So Frege said, no, there's no such thing. Concepts are nothing but properties, which led to the disaster known as 20th century set theory. Sorry to exaggerate that way. And it was a disaster partly because it led to ignoring Cantor's original point of view about it. And its relation to, fortunately, mathematicians at large stuck with Cantor's viewpoint, but they didn't, not in a formal way. Anyway, and then after the great pedagogical triumph of Lawvere, the which people are trying to tear down now under the guise that it's not beautiful or something stupid. But nonetheless, there was the idea, well, everything is a structure. Well, there's a nice paper of Max Kelly and Steve Lack about structure or property. It turns out that according to them, there are 12 different ways that those two things could be combined. We often, for example, we often in category theory define a property to say that an already given map is invertible. So, you see, but that the inverse is a structure, but it's unique. So, there are about 12 cases. Anyway, so I think the philosophical explanation should be, according to my present viewpoint, just like a space is an object in the spatial category, a mathematical object or concept in general is just an object in the category. Prima di tutto, you see. But then the thing about structure is you can represent objects as structures. And this is a basic example of it. I can represent X as this category, and if my figure-shaped notion is adequate, then I've quite well represented the structures, the objects of X as structures of that kind. But I could equally well maybe choose quite a different A with the same result. So a full and faithful representation of E as A-shaped structures or as A'-shaped structures. So to say that the object is a structure is wrong because it is. But it's an object. And then of course properties come in because the discrete vibration is the same thing as a presheet, by the way. I should have said it maybe that way if I'm more used to that. We come sort of directly to this category, but it's also a presheet over A. There's the property, well, which presheets over A are going to arise as objects of E? So this is where properties come in, or one of the main places where properties per se come in. So if structure and properties have a dialectical relation, they are a kind of higher-order presentation of a concept rather than the same thing as a concept, because you can have different pairs, A, property, which all succeed to capture all of E. And of course the interesting thing is that a very big E can be captured by a very small A in many cases. And so the thing becomes attractive. When am I supposed to stop? Mark? I don't understand. More or less. Okay, let me see if there's a natural stopping place here. The answer to that is no. Well, okay. Obviously, there's a dual idea where we represent E op in terms of things like this, and this is called a function algebra. It's an op vibration instead of just a vibration over A. And a morphism here is really nothing but an algebraic operation, like squaring, cubing, taking the sum of two if you have products and so forth. So the algebra of functions on X with certain types. I call these things types, as in logic, as opposed to shapes. The objects can serve either purpose within a certain analysis. So this is precisely the function algebra of X. And again, it often happens, if you choose the A properly, then E op may be adequately represented in terms of function algebra. And homomorphisms of function algebras are just, maps of vibration. So there The same objects might be analyzable as algebras or as spaces. And the examples that we're interested in, it turns out that a small idea of figure shape is much better than algebra, because what I'm saying is that even though, let's say you consider toposes, a natural choice of algebra is hiding algebra, the truth value. See? But if you consider only that, it's not co-adequate. Even if you consider all the powers and so forth. So typically the omega is not even a co-generator in the weak sense that you get a faithful representation. There's some examples of considerable importance where it is faithful, but it's never full, due to the famous measurable cardinals. It's closely connected with having a small co-adequate subcategory, in Isabel's terminology, is a statement that measurable cardinals are not inside my category, more or less. So now that what we are, I'll start here. But what implicitly so far I've been talking about U-toposes in the sense of rotating. So the next step is to figure out what U is. And this will be, in order to achieve Grossman's program,